Okay. Today's lab will be introduction to microwind, layout design of a CMOS inverter. That means in our previous classes, we have actually covered PSpice, excuse me, and DSCH. PSpice is a, what is that? A code-based or command-based simulation software. DSCH was a schematic-based, what is that? Simulation software. But in microwind, we will be designing the layout. What is layout actually? Let's go to the Google and see what is layout. Mask layout. Okay. Not this mask, not this. Mask layouts are these. Okay, these are the mask layout. Can you see that layout? These are the mask layout. What are these actually? Okay, let's write Core i7 mask layout. Core i7 mask layout. Okay. This is AMD mask layout. AMD maybe, I'm not sure. AMD or Core i3, I do not know. This one is, which one? Nephalon processor. From Intel. Okay. So these are actually what? These are actually your processor design. These are your processor. Can you see some different colorful things? These are actually all layers, all different layers. So that we have already seen here. Here, right? The mask layout. Can you see some colorful things? Green, blue, red, purple,
yes,
all those things. This is a very simple and very small design, small layout. Maybe 4 to 5 transistors are there. 4 to 5 transistors are there. But in your Core i3 or Core i7, Core i5, something like that, you have millions of, or not millions, actually billions of transistors. You can see, right? If you design billions of transistors, you cannot see any pattern. You can only see colors. But my point, you have to see, if you want to see the pattern, you have to zoom it. Then you can see it. Understood?
Yes, sir.
Okay. This mask layout will be then transferred by using lithography, that we will learn later. What is lithography? Will be transferred by lithography process to silicon. Got my point? That time you will have these. That time you will have something like this. This is inside a microchip or an IC. Can you see it? Inside an IC, you have something like this. Can you see some pattern there? Some design pattern?
Yes. If you zoom
Here, if you zoom, can you see some patterns?
Yes, sir.
These are actually your layout design. So at first, you will do the layout design inside your computer. Then using a sophisticated, very expensive machine, you will transfer that design to silicon. This is the silicon. You will transfer that design here. That's it. Pretty simple. Understood?
Yes, sir.
Okay. So which one is tougher? Designing the thing is tougher. So as an engineer, as a VLSI engineer, you will be designing the things. You will be designing these layouts. Okay? This is a layer.
Yes.
Can you see the color? Can you see the color? Colorful things? This is
Yes,
a layer.
sir.
This is a very
Green.
big. This is a very big layout. So today we will be learning about what? Learning about mask layout design. Okay. So at first we will start with the very basic one. What is the basic one? CMOS inverter. Pretty simple. Not get. Understood? Pretty simple. Not get. Okay. CMOS inverter. Okay. What are the objectives of this lab? To manually design. Why I am saying manually design? There is one more trick available, one more design available, that is called automatic design. Automatic design, we can do the automatic design to some extent using DSCH. Have you seen the DSCH? The software we have used for lab number 7, 8, 9, and 10. We can use the software to use or to generate automatic design. But today we will learn about manual design, not automatic. Automatic design are there, very easy. But today we will learn the manual design. Understood?
Manually.
Manually. To manually design the mask layout of CMOS inverter. Number 2 is to check the design for design rule error. That means whether there is any error or not, we will check it. to check the functionality of the inverter using simulation with built-in simulator. That means whether our design is working or not. Maybe there is no error, but it is not working. It can happen. There is no error, but it is not working. Got my point? It can happen. So we will check two things: whether there is any error or not, whether it is working or not. Understood? Okay. Number 4, to extract the net list from the inverter. Okay. To perform the simulation, net list is something else. We will talk about that later, not now. Now, to CMOS inverter, what is CMOS inverter? We have one NMOS, we have one PMOS. If we connect them together, what happens? We got a C inverter, right? We got a NOT gate. This is our NOT gate, right?
Yes. Yes, sir.
You already know it. Now here, manual design. There are some procedures are given. Procedures, right? I have written those procedures for you, so that if you miss the class, you can read those and what? And do it by yourself. But I'm not going to read those because I have already written those, right? Today I'm going to show you. You just see. Okay, these were written for what is that? For normal classes. That means when there were no videos. Now you have videos, right? So I do not have to read all of those. You can read by yourself. I remember I have written all of those. This is my writing. I didn't copy it from somewhere else. This is my writings. Okay, so this is
Yes,
there.
sir.
All the processes are given. Then simulations are given. Whether our design is correct or not, there is some what is that? This is a button. If you click the button, it will tell you whether there is any error or not. The netlist, you can extract the netlist, then save an output. That's it. Okay, I'm going to show you how to do it.
Okay, sir.
Let me go to the software. This is the microwind. What is microwind? I have given you one software, right? This software. Remember DSCH, microwind, OrCAD. Here,
Yes, sir. Yes, sir. We
DSCH
have.
and microwind, you do not have to install. It is already installed. So whatever you do, copy the whole folder and use it. OrCAD capture, this is the PSpice. You have to what? You have to install it. Okay. Now here microwind is already there. So if you click the microwind, there are 4 folders: example, HTML, rules, and system. So go to the system, click the microwind. Can you see that microwind?
Yeah.
31.
Yes, sir.
Click it. Is it familiar?
Yeah,
Yes. Yes, sir.
just is familiar.
Just like what?
DH.
Exactly, just like DSCH. Because DSCH and microwind, they are actually made by same company.
Yeah.
Okay, that's why they are similar. Here you have one palette. If the palette is gone, you can click here. Can you see the palette? The
Yes, sir.
rainbow. Click here, it will come up. No problem. Oh, by the way, before starting, remember when you just start, one thing you have to do. What is that? First thing, go to file, then click select foundry. Select. First thing,
Okay.
after opening the software, go to file, select foundry. Then you will have no, not this. You have to go to the microwind folder, then rules. Okay. If your rules folder already opens up, you do not have to go anywhere else. If do not, like mine, you have to go to the which folder? Rules folder. Remember, we have
Rules
seen
folder.
the rules folder. Where? Here. We have to go to the rules folder and we have to click the CMOS 90 nano. Can you see that? CMOS 90N.
Yes, sir.
That means it is 90 nanometer rule. 90 nanometer. You have to go to the 90 nano. Why? Because all the calculation I am going to show you, that is for 90 nano. If you use different rules, your calculation will be different. Understood? Understood, my dear?
Yes, sir.
Okay. So you have to click.
So we use 90.
Yeah, you have to do 90. You can do other as well, but that time your calculation will be different. What calculation? The size and width, the length, everything else will be different.
Yes.
So CMOS 90 nano, you have to click open. So after opening it, can you see at the top right corner, it is called 1 lambda.
Yes.
Can you see that?
Yes, sir.
1 lambda. If your lambda is not 1, maybe you can have something like this. No, not this. Maybe you'll have something like this, 5 lambda or maybe 10 lambda, depending on your computer screen. My screen is too, what is that? The resolution is high. That's why it was 1 lambda. But for you, it can be 10 lambda, 5 lambda, 100 lambda, 1000 lambda, something like that. So what you have to do? You have to zoom in or zoom out to make it 1 lambda. When it is 1 lambda, you stop. Copy point?
Yes, sir.
When it is 1 lambda, you stop. You can zoom it as well, no problem. Okay. This is 1 lambda. Can you see 1 lambda? So when it is 1
Yes,
lambda, that time your calculation will be correct. Okay,
Yes.
remember 1 lambda. 1 lambda means 1 slot. 1 lambda means 1 slot. Here 1 slot is 1 lambda. Okay. Now before going into there, I'm going to show you something else. I'm going to show you in a whiteboard. What is an NMOS actually? Oh, no, what is an CMOS actually? CMOS actually like this. Okay, let's use different color. Okay, got my point? This is what? This is P type. No, this is not P type. This is N type. No, I made a mistake. This is P type. This is N type actually. Okay, now see. Hello?
Yes, sir.
Okay, wait a second. This is silicon dioxide. This is also silicon dioxide. Then you might have a metal. What is the metal? Okay, let's give this as a metal. This metal is not mandatory. You can actually skip it. Then you have a metal pin here. You have a metal pin here. You have a metal pin here. Okay. Now this part, let me go. This part is N well, N type. Okay, N minus actually, N well. This is an N well, N well. Well means what? Do you know well? Well is something where the water is there, right?
Yes, sir. Yes, sir.
Well, N well. This is an N well. Okay. This is,
N-type well.
yeah, this is P type.
B.
P type material. This is N type material. So this is actually N plus. Okay, let me use different color. N plus. This is N plus. What is plus? Why plus? Why minus? Plus means heavily doped. Minus means very lightly doped. And normal means normally doped. Okay.
Yes.
Or you can say you can call it P type as well. You can call it P minus. This one, this is P plus. P plus. Okay. Now what is this? The yellow one. Yellow one is silicon dioxide. What is that? Silicon, or you can
Yes,
call
sir.
it polysilicon. Silicon dioxide or silicon. Now this one is source. This one is source. This one is drain.
Gate.
This
Gate,
one
yeah.
is drain. This one is gate.
Gate.
This one is gate. Okay. Now look at our design. This is our design, right? Here, what we have, this is our source. This is for PMOS. This is our what? This is our drain.
Drain.
This is our drain. This is our source. This is our gate.
Gate.
This is our gate. Can you see that? So gate are connected. So this gate and this gate will be what? Connected?
Nothing.
But you can connect it using metal wire, or you can connect it using polysilicon, your wish. You can connect it by using metal wire, or you can use it you can use what? You can use polysilicon, your wish. So we are going to use polysilicon. Okay, we will call it internally connected. That means same polysilicon will go to the here and here. Then what? Drain will be connected. Drain. Okay, let's connect the drain. So drain is connected, and our output will be from here, right? See?
Yes, yes.
Okay. And our source, which source? PMOS source. Which one is PMOS? This one is PMOS, because this is
Yes.
P plus. So this source will be connected where? To VDD. VDD source.
VDD, yes.
VDD, right? And this
Yes,
source
sir.
will be connected where?
Ground.
Ground. Yeah.
To ground. Got my point?
Yes,
This is the
sir.
main connection that we are going to use for our design. So at first, what you need, you have to understand. Okay, let's go to the screen. Here, what you have to do, you have to dedicate one area for your PMOS. So that time you have to use P diffusion. Can you see here? It is written P diffusion.
Yes.
Can you see that? Okay, I'm going to click P diffusion, and I'm going to take the P diffusion like this. How many? This is 10, 11, 12. 12 is there, and here how many? 1, 2, 3, 4, 14. So the what is that? The dimension will be 12 lambda. Lambda means what? One lambda means one slot. So how many slots you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Understood?
Yes,
So
sir.
12 lambda. And this dimension is how much? 14 lambda. Okay, wait a second.
Maybe 60, sir.
Okay, wait a second.
15.
Full row.
Hello, understood?
Yes, sir.
Okay, I was shouting by switching off my microphone. And I was thinking what happened. You understood, right? It is 14. Okay?
Okay.
Yes, sir. 14
now-
and 12.
Yeah, this is 12, this is 14. Okay. This, what is that? This measurement is very, very important. Why? Because see, this is P type and this is N type, right? So P is at the top, N is at the bottom. Got my point? What is the sizing of these two? This is 2, this is 1. Remember 2:1? Remember 2:1, right?
Yes, sir.
2, what is 2?
Yes, sir.
2 is, that means the width, double width. This is 1W. If it is 4 micro, it is how much?
Will be
8 micro, remember?
8.
8 micro. If it is 6 micro,
Yes, sir.
how much is this?
It will be
12.
12.
So if it is 6 lambda, how much is that?
24.
No, 12.
12
Oh.
lambda.
6 lambda, 12
12.
lambda. That's why it is 12 lambda. This is width. This is length. This is L, this is width. Understood?
Yes, sir.
Okay. Now see. Now I'm going to use the N diffusion. N diffusion for NMOS. Here for this. Click N diffusion. So we have to give a 12 lambda gap. 12. This is 8, 9, 10, 11, 12. So 12 gap. Minimum 12. Maximum you can go for a lot of gaps. No problem. But minimum should be 12. So I'm going to give 6. So this is 14. This is 6. Yes. Okay. So again, see, you can see this is how much? This is 6. How much is this?
6.
14. This is 14.
14, yes, sir.
This is how much? 12.
12.
So you can see that this is NMOS. The length and length are same, right? I told you before, length and length will be same. Remember?
Yes, sir.
In our
Yes, sir.
first lab,
Yes,
length
sir.
length will be same, but the width will be double or triple. Here in this case, let's consider double. So if it is 6 lambda, it will be 12 lambda. Okay?
Yes, sir.
You can ask me, sir, why it is 6 lambda? Why not it is 4 lambda? You can ask me, right? Can you? Anyone has
Yes,
this
sir.
question? Why it is 6
Yes.
lambda? Why it is 14 lambda? Why not less than that? Why
Yes,
not more
sir.
than that? Okay, I'm going to explain. Here, I need to make some gate, that is polysilicon. Okay? Polysilicon is this one. Can you see the red color polysilicon?
Yes.
Okay, I'm going to click the polysilicon and I'm going to give the polysilicon here. Yeah. So I'm going to erase this, otherwise you will be confused. Okay, I have given a polysilicon. Then why it is 2 width length? What is the width of this? Why it is extra? Because there are some rules. The rules is you have to give at least 3 lambda extra, 3 lambda extra. Here 3 lambda extra. Okay, at least you can give more than 3, but not less than 3. Okay. So why I am giving you this? Okay, if I want to make it smaller, can you see there is a button called move or stress? Here, if I click this, and if I click these, I can make it up. If I click this, I can make it down. So if I give 2, can you see that 2? If I give 2, not 3, then there will be an error. See why it is saying 3 lambda? Can you see that?
Yes,
The
sir. Yes,
extra
sir.
polysilicon should be 3 lambda. So that's why I have given 3. I'm going to click here and I'm going to make it 3. Okay.
Sir, maximum?
Maximum you can go for 5, 6, 7, no problem. But we will
Okay,
avoid
sir.
the maximum. Why avoid maximum? Because we want our design to be as small as possible. Okay? We want
Okay.
our design to be as small as possible. That's why we will avoid what? Avoid maximum.
3.
We will do the minimum one. Now, why it is 2? It was more than 3, I understand. Why it is 2? Because we want to give our input in our silicon, right? This is our gate. The red one is our gate. We want to give our input here. So input is, what is our input? Maybe this is our input. Can you see it is two segment? Can you see that? It is 2 by 2. So if I give it to here, so I need at least 2, right? Can you see that?
Yes, sir.
This
Yes, sir.
this
Yes.
square box is 2 by 2. So
Yes.
your polysilicon should be at least 2. That's why it is 2.
2 by 2. Yes, sir.
Yeah.
Now here, so you have to give 6 lambda and 6 lambda gap here. So here, the gap should be 6. Here, the gap should be 6. Why? Why? Because I want to give this one. I want to give these. This is square box. Can you see the box? I want
Yes,
to give
sir.
this square box. This is square box. This square box needs 4 lambda. How much? This is the
4
square box.
lambda.
Can you see the box here is NP, right? NP. Can you see the NP?
Yes, sir.
Okay,
Yes, sir.
I'm going to click the N for NMOS. You understood why I have given 6? Because itself it is 4. So you have to give 1 extra, 1 extra. Here you have 1 extra, 1 extra. So that's why it is 6. That's why it is how much?
6.
Here you have 6. Here you have 6. Here you have 2. So how much is this?
14.
14. Understood why it is 6 and 14?
Yes,
Hello?
sir.
Oh. Now let's bring the NMOS again. One is source, one is drain. You have to be at the middle. Then for PMOS, click P, bring it here at the middle. P here at the middle. Understood? But you can see here it is extra. Because why it is extra? Why it is extra? Because it was 6, it should be more than 6. That means double. That means 12. Extra is not a problem. Extra is not a problem. Okay.
Okay, sir.
Okay. Now we have to connect. We have to what? We have to connect. How to connect? See this one. This is our gate. Gate is already connected by using what? By using polysilicon. Okay. Now this is your source. This is your drain. This is your drain. This is your source. Okay.
So drain is connected.
Which one is your source? Which one is your drain? This is source. This is drain. Which one?
Sir,
Let's consider this is our
right.
source. This is our drain.
Right, sir.
This is our drain. This is our source. Okay. Let's consider like that. If you want to switch it, you can do that. No problem. Okay. Now here, drain must be connected, right?
Yes, sir.
Yes, sir.
Okay. That means these and these should be connected. By using what? Using what?
Polysilicon.
No, not polysilicon. Polysilicon is what? Polysilicon
Only
is for
gate.
gate. Yeah, only for gate.
Okay.
This one should be metal.
Okay. Okay, sir.
Metal. So I'm going to click which metal. Can you see here? You can see you have how many metals? 1, 2, 3, 4, 5, 6.
6.
I'm going to use metal 1, not 4, 5, 6. Why? Because this contact, can you see the contact? These are for metal 1. So I'm going to use metal 1. Okay, like this. Okay.
Okay, sir.
Remember,
sir.
the metal must be at least 3 lambda. At least. If it is more, if it is 2 lambda, there will be a problem. Okay. 2 lambda means very small, and that will increase the resistance. Okay. So it should be at least 3 lambda. We have given how much? How much we have given? 1, 2, 3, 4. Okay, we have given extra, right? Okay, it's problem. No, it's no problem. It's not a problem. Okay, it's not a problem. Okay. Now here, at the top,
Source.
at the source, what do you have?
VDD. Connected
VDD.
VDD.
Okay, I'm going to give VDD. What is VDD? Which one is our VDD? This one is our VDD. First one, VDD supply.
That one, blue wire.
VDD
Here.
supply.
You can give it here, or you can take a wire or give it there. No problem. I am going to give it here. Okay. Double click. What is the voltage of VDD?
540.
5.
5. What? But what is given here?
Given is
1.2, right?
yes.
Here the given is 1.2. I need 5, so I'm going to click 5. I need 5. I'm going to give 5. Okay. Okay.
Okay,
I'm going
sir.
to give 5. Okay. Assign. Now, what is our ground? Ground is the NMOS source. That means this one. Right? What is our
Yes, sir.
ground?
Fine.
NMOS source. Here. So I'm going to click
Yeah.
the ground. Where is ground? This is the ground. I'm going to click it here. Or what you can do, you can actually like this. You can take the metal like this. Then you can give your ground there. Okay, your wish, but I do not like it. I want this one is a simple one. Okay, understood?
Sir.
Now we not forgot actually, we didn't do one more very important thing. That is what? That is actually this one. No. We have actually given there is an area, right?
Yes, sir.
The whole area was P-type. Then we dedicate one area for our what? For our PMOS, right?
Yes,
The
sir.
whole thing was P-type. Then there we develop our N-type. But we have to dedicate one place for our what? For our P-type. So this is called N-well. So this is called what?
N-well.
N-well. Okay, I'm going to go for the N-well. What is our N-well? This is the N-well. Can you see the N-well last one? Click the N-well. The N-well should be here. So N-well should be 1, 2, 3, 4, 5, 6. 6 by 6. So here 1, 2, 3, 4, 5, 6. Can you see that? Here 1,
Yes, sir.
2, 3, 4, 5, It should be 6 as well, but I made a mistake, right? So I need to make it 6. So how can I do that? Click this button, move or stress. Click it. Which one is small? This one is 6. This one is 6. This one is 6, right? Which one is not 6? The bottom one is not,
This
not
one.
6.
Yes.
So I'm going to
Ah,
click
it's
the
fine.
bottom boundary. Click it. Okay? This is called
Yes.
correction.
Yeah, I don't know.
Understood?
Yes, sir.
This is the N well. Remember, the N well needs a VDD as well. N well needs a VDD as well. So where? Anywhere. Here, let's give the here. Double click, it should be 5 as well. So you have to give 2 VDD. One is for actual VDD and another one is for N well VDD.
Well,
And
Okay,
well.
both of them will be 5 volt. Now we have to give the input and output. Where we will give our input? Where we will give our input?
Between two drain.
So,
Yeah, no, not drain. It should be in the gate. It should be in the gate, right?
Yes, sir.
It should be in the gate. So input is this one, the clock. Can you see the clock? 1, 2, 3, 4. Number 4 is the clock.
Yes, sir. We see.
I'm going to click and we are going to give it here. The polysilicon or here. I like here. Double click. The name of the clock should be A. And the voltage should be what? 5. And low time, rise time, high time, fall time. Okay, you do not have to touch it. Just you can keep it like that, or you can play with it. No problem. Assign. I need an output. What is our output? You tell me which one is our
Yes.
output. From where we drain? We take our output from drain.
Between drain, sir.
Between drain. Which one is our between drain? That is this metal.
This metal, yeah.
Okay, here we will put our output. What is our output? Output is the last one. Can you see an I? An I symbol, I. I means
Yes,
see,
sir.
visible. I'm going to click and I'm going to place it here. Double click. The name should be Y. A and Y, assign. So this is our final design. Okay, let's check whether there is any error or not. So if the design is very big, you can click all. All means the whole design will come in the same one spot. All. If you click all means what? Like that. If your design is very zoomed, if you click all of it will come in the one screen.
Yes,
Now
sir.
we want to check whether our design is correct or not. I'm going to click DRC. There is a button called DRC. Can you see that? DRC. I'm going to click DRC. No error. If there was any error, it could have been there. Okay, let's create an error. Let's create an error. 1 error, 2 error. Okay, let's see. Here, can you see there is an error? Why?
Yes.
Yes,
What?
sir.
If I click all, okay. If I click DRC, there will be an error. They said it should be less. It should be 6 lambda. So if I click, make it okay now. If I click all, now this error is fixed. Click. There is another error, right? Now it is fixed. Go to the all. Click DRC. No error now.
No,
No error. Now check whether our simulation is correct or not. Click run. Okay, this is a very big one. Okay, let's make it 2 nanosecond. Okay, now can you see? Okay, what is our green? This is our green. Can you see this is 0? Like that?
0505, yes.
Can you see that? Okay, now for red one is our output. So for 0, your output is 1. For 1, your output is 0, right?
Yes.
Can you see that?
Yes, sir.
013. No, 00.
Okay, can you see that? Okay, now here there is a problem. Problem is you can see some output at the middle. There are some glitches, right?
Yes.
So and the first cycle is not correct. Not correct means not perfect. The first cycle is not perfect. Why that happens? Because we are doing manual design. Manual design has this sort of problems. If we do the automatic design, it will not, there will be no problem. Okay? I will teach you the automatic design after the exam. After the exam means after this exam. Otherwise, all of you will go for the automatic design. I know that. Understood?
Yes, sir.
Automatic design is so simple. That's why maybe all of you will go for the automatic design. No, I do not want that. I want you to do the manual design first. So this is the design, and our design is correct. And I hope you can do it right now if you want. Not if you want, you have to do it. All of you, take some time and do it. Okay?
Okay, sir.
Okay, I'm going to give you 10 minutes of time. Okay, I'm going to pause the recording. Okay, now here, since we have done the lab number 4, that means the
Yes.
CMOS inverter, let's go for the next one. That means lab number 5. This one. Layout design of a NAND gate and a NOR gate. So I'm going to do the NAND gate for you. You will do the NOR. Okay?
Okay, sir.
Okay. Now, what is NAND actually? NAND is this one. This one is NAND. So what is the output? A, B bar, right? So truth table will be 0, 0 means 1, 0, 1 equal to 1, 1, 0 is equal to 1, 1, 1 is equal to 0. So if we do the CMOS representation of our NAND gate, this is the design. So this is our PMOS, PMOS, NMOS, NMOS. This is 2, 2, 2, 2, right? So we are actually considering 2:1. That's why it is 2, 2, 2, 2. Remember, our 1 is equal to what? 6 lambda, right? So our 2 will be what? 12 lambda. So this one will be 12, 12, 12, 12. This is easy. So all of them are 12, 12, 12, 12. So, oh, by the way, length will be 14. This is fixed. Length is fixed. This is a width. Now let's go for the transistor level. Remember, you have A. For A, you have one PMOS and one NMOS. Both of them are 12, 12. For B, you have another PMOS and another NMOS. And again, both of them will be 12, 12. So let's design those first. So I need new one. I do not want to save it. So again, I'm going to select the foundry. Okay, since it is already selected, so I do not have to select again. So, but if you start from the beginning, you have to select it and you have to go for the lambda 1. Okay, understood?
Yes, sir.
Okay. Now I need to select the PMOS, P-diffusion. So I'm going to make it what? Make it how much?
14.
12 and 14. So this is 10, 11, 12,
12.
13, 14. So this is 11, 12. Okay? So this is 12, this is 14. Understood? Now I need to do the NMOS. Again, it is 12 and 14. So gap will be minimum 12. So this is 8, 9, 10, 11, 12. This is 6, 7, 8, 9, 10, 11, 12. Okay. So this is what? This is our NMOS and PMOS. Again, now I need what? Polysilicon from the beginning, from the middle. So the middle, deciding the middle is very important. Remember, I know what is the middle. This is the middle. If you do not know which one is middle, you can always correct it by using the expand. You can move, right? Now I need to use the NMOS. That means N contact. This is the N contact. This is P contact. This is P contact. Now this is for A or B, whichever, doesn't matter. So I'm going to copy it. Why I'm going to copy it? Because both of the sizing is equal. So 2, 2, 2, 2. So since their sizing is equal, I can copy it. How to copy it? There is a copy element button. I'm going to click. I'm going to select from the bottom, not from the top. Remember, from the bottom, the whole thing, so that the whole thing is covered. Bottom up to this. Can you see the whole thing is covered, right?
Yes, sir.
Copy.
Yes, sir.
Now I'm going to copy it. Remember, the gap should be minimum 6. 1, 2, 3, 4, 5, 6. And they should be what? They should be aligned. Remember, they should be aligned. If they are not aligned, your NMOS will have a problem. Sorry, N well. Now the N well. I'm going to give the n well to whole A and B. So A, 1, 2, 3, 4, 5, 6. N well, 1, 2, 3, 4, 5, 6. Okay, done. Now 1, 2, 3, 4, 5, 6.
6.
Okay. So is there any no error? So this is what we have done. Now we have to know which one is our drain, which one is our source. Let's say this is what. Okay, I'm going to use the white color. This is our source. This is drain. This is source. This is drain. Okay. How I am selecting this? My wish. I always select the left side as source, right side as drain. You can do the opposite one as well. Your wish. This is source, drain, source, drain. Okay. Now bring the design. Before bringing the design, okay, let's do the design here. Let's do the design. Here, NAND gate, right? So they should be parallel. Here they should be what? They should be series. Okay, now remember this is your output. Now our gate is not important because gate is already connected. So which one is our important part? See, this is our source. This is source. This is drain. This is drain. This is source. This is drain. This is source, right? Now you can see the PMOS side, source is connected, drain is connected, right? See, source connected, drain connected, right?
Yes, sir.
Yes,
So
sir.
I'm going to do what? I'm going to connect the source and connect the drain. Understood?
Yes, sir.
Okay.
Yes, sir.
Now see, this one not needed, not needed, not needed, not needed. So I'm going to click the metal one. So I'm going to make a path. Remember one thing, this gap should be at least 4 lambda. Okay, this gap should be at least 4 lambda. That's why I have taken a path this way. I could have gone like this. I could have gone like this. But that time there will be no 4 lambda gap. Understood?
Yes, sir. Yes, sir.
So okay.
4 lambda.
So this one again, this is for source is connected. Now drain should be connected.
Drain.
Again, I have to give 4 lambda gap here. Okay, let's check whether it is. So for A. Oh my God, no, made a mistake.
Delete.
Okay, here I know it is more than 4 lambda, so you don't have to count. Okay, it is 5 lambda maybe.
Yes.
The gap is 5. Okay, now check for any error. No error. Now for the bottom part, you can see which one. Here you can see the upper drain and the lower drain. That is what drain it is. This is A. This is B. Let's say this is A. This is B. Understood? A, B, A, B. So which one is our A? Which one is our B? You decide. Which one is our
Number
A?
one
Which
is
one is
A.
our... The left side is our A. Let's say.
Left side, yes. Left
Okay,
side.
this is our A. This is our B.
B.
Right? Now here, drain
Drain
and
is
the A
connected
drain
to
should be
drain.
connected. The upper drain is this one, and the A drain is which one is A drain? This one is A drain, right?
Yes. Yes, sir.
So they should be connected. Understood?
Yeah.
Now then, A source and B drain are connected. A source, B drain. Which one is A source? A source is this one. Which one is B drain? This one, right?
Yes.
They should be connected. Now, B source should be what?
Ground.
Ground. So here should be our ground.
Ground.
Here should be our ground. And the topper and the top source. Can you see the top sources? That means this one should be our what?
VDD.
So here should be our VDD. And we have one more extra VDD. Which one is extra VDD? This is our extra VDD.
And
And
1.
where we will take our output? We will take our output from here. Because it's
between.
drain. Okay, between.
Drain to that.
This is our input A. This is our input B. That's it. Understood? Let's design. Now we need what? We need metal 1. Select up to this. Fine. Now these.
Source to the brain. Yeah.
Okay, done. Done. Okay, is there any error? No error. Okay, now anything else? Anything else? No, nothing else. So we have to
Ground.
give our source. No, give our
Ground.
ground. Here is our
Ground to
ground.
the S. Yes.
This is the VSS. We have to give our VDD. Where is our VDD? Click the VDD, give it here. Or here, or here, or here. Doesn't matter. Double click, it should be 5 volt. Now we have to give another VDD. Let's say here. Double click, 5 volt.
And well.
Now we have to give input A and B. Okay? Well, here, the clock. I'm going to give this one. The name should be A. And the voltage should be 5 volt. Can you see the voltage? 5 volt.
Yes.
Next one, click,
Output.
not output, B. The voltage should
Yeah.
be B.
Input. Yeah.
See, the time is already doubled. Remember lab number 2, lab number 3, lab number 4? No, lab number 2, lab number 3, the time was double. A and B, the time was double, right? Here, the time is automatically double, so you do not have to double it. It is already doubled.
Yes. Yes.
Okay.
Of course, yeah.
Only the thing you have to change, that is the level V. Level,
Yeah,
that means the level of voltage.
yeah.
It should be 5 volt. I think everything, oh no, output is not there. So this is the output. Click the output and give it here. The output, let's call it Y. Okay? Now I do not need any more design. I'm going to erase everything. So this is your design. Your design is completed. Understood?
Yes.
Now let's check whether our design works or not. Okay? Okay, no error. I'm going to click run. Okay. Okay, here you can see the white color. This is the white color, then the green color. Okay, now the red color. All of them are 1. This one is 0. 1. Okay, now check. This one is what? This one is 0, 1, 0, 1, 0, 1, 0. This one is 1, 1, 0, 0, 1, 1, 0, right? Next one, this one is what? This one is 1.
1.
0 1 1 0 1 1.
See, here, look at this case. When your input is 0, 1, your output is 1. When your input is 0, 0, your output is 1. When your input is 1, 0, your output is
1.
1. When your input is 1, 1,
Output 0.
output is 0. So your truth table is correct, right?
Yes, sir. Correct.
NAND gate. So this is how you check. Understood, my dear?
Yes. Sir.
Yes, sir.
So I believe you can do it. I believe.
Yes, sir. Yes, sir.
Okay. So I'm going to pause the recording.